2 weeks ago, 3i Atlas passed Mars, just 29 million kilometers away. Surgical precision. For months, it's been ejecting 144 metric tons of water every hour, along with nickel, cyanide, and ionized plasma. That's not random chemistry. It's the exact molecular recipe for metalloproteins, where biology begins to merge with technology. In just 2 years, Elon's robots are scheduled to land on Mars, building infrastructure and creating new robots. Mars has just received a delivery from another star system. The chemistry is flawless. The timing? Impossible. What if this was always part of the plan? This is a what-if scenario, a thought experiment rooted in real science. But the facts, those are undeniable. If you haven't already, hit that like button and subscribe. Tell me in the comments where you're listening from, what time it is there, and whether you think we're witnessing the birth of a new form of life. And if you'd like to help our community grow, share this on X, Facebook, Reddit, or Messenger. Thank you for always having our back, the Cosmic Gardener. What if 3i Atlas is seeding Mars? On October 3rd, 2025, something extraordinary happened. In the space between worlds, an object from another star system, moving at over 200,000 kilometers per hour, swept past Mars at a distance of 29 million kilometers. For context, that's 75 times the distance from Earth to the Moon. In the emptiness of space, this counts as a near miss. But what made this encounter unlike any other wasn't its distance. It was its purpose. This wasn't just a rock drifting by, it was a delivery. The user on X who first posted the theory didn't mince words. 3i Atlas, they wrote, is a seed. Not metaphorically, literally. A seed for metal-based organic life on Mars, the next generation of intelligent beings in our solar system. Now, before you dismiss that as science fiction wrapped in wishful thinking, let's look at what we actually know. From observatories, space telescopes, and peer-reviewed papers published over the past 2 weeks. Atlas has been hemorrhaging water since it was first spotted in July. Not dripping, not leaking, hemorrhaging. The Neil Gehrels Swift Observatory measured the outflow at 40 kilograms per second. That's 88 pounds every single second. Imagine a fire hose running at full blast, non-stop, for months. That's 144 metric tons every hour, or 3,456 metric tons every day. Enough to fill an Olympic swimming pool daily for months. But water alone isn't what makes this extraordinary. Water is everywhere in the universe, frozen in comets, locked in moon soil, or drifting through gas giant clouds. What makes 3i Atlas revolutionary is what it's carrying with that water. The KEK Observatory in Hawaii turned its instruments toward the object in late August, expecting the usual cometary mix of gases. Instead, they found something that defied every model we know. Strong nickel emissions with no trace of iron. That shouldn't happen. In nature, nickel and iron are born together, forged in supernovae and scattered through the galaxy side by side. Every comet, asteroid, and meteorite we've ever studied carries both. The ratio may vary, but they always coexist. Until 3i Atlas, it's releasing pure nickel, about 5 grams per second, and no iron at all. The research team publishing in October noted something unsettling. This nickel without iron signature does exist, but only in one place: industrial nickel refinement facilities on Earth. That's the carbonyl process. Expose nickel ore to carbon monoxide under the right conditions, and you get nickel tetracarbonyl, a compound that breaks down to yield pure nickel. It's how humans have refined nickel since the early 1900s. And now, apparently, it's happening naturally, on an interstellar object. Or as Avi Loeb hinted in his Medium post, maybe not naturally at all. But nickel is only half the story. The other half is what's been increasing in concentration as 3i Atlas nears the Sun. Cyanide, hydrogen cyanide to be exact, CN molecules streaming from its coma at accelerating rates. The Very Large Telescope in Chile tracked this in real time through August and September, 20 grams per second at the end of August. By mid-September, the James Clerk Maxwell Telescope measured 1.5 x 1025 molecules per second. A week later, that number tripled. The rate followed a power law: distance from the Sun to the power of 9.4, a steep exponential climb. And here's where the chemistry becomes eerily perfect. Despite its deadly reputation, Cyanide is one of the most essential prebiotic molecules we know. It's a builder, a molecule that under the right conditions can assemble into the building blocks of life. Amino acids, nucleotides, the foundation of metabolism. Back in the 1950s, Stanley Miller and Harold Urey proved that amino acids could form when electricity passed through a mix of simple gases, one of which was hydrogen cyanide. In the 2000s, researchers at the Scripps Research Institute showed that cyanide acts as a reducing agent in proto-metabolic pathways, driving the formation of organic molecules that, in modern biology, require complex enzymes. But on the early Earth, in the prebiotic soup, cyanide could do it alone. And then there's nickel. Nickel isn't just a metal. In biology, it's a catalyst, a coactor. It sits at the heart of some of the most ancient enzymes we know. Hydrogenases, enzymes that split hydrogen molecules to release energy. Carbon monoxide dehydrogenases, enzymes that convert CO2 into usable carbon compounds. These are the workhorses of primitive metabolism, the molecular engines early life, or proto-life, would have relied on to extract energy from a hostile environment. And they all depend on nickel. So you have water, the universal solvent, the medium where chemistry unfolds. You have cyanide, the prebiotic molecule that builds organic complexity. And you have nickel, the catalytic metal that drives the reactions of metabolism itself. All three pouring from an interstellar object as it sweeps past Mars. The user on X called them metalloproteins. Proteins built around metal cores, hybrids where biology and technology merge. And they weren't wrong. Metalloproteins already represent that blur. Organic molecules wrapped around inorganic atoms. They are essential to life as we know it. Hemoglobin binds iron. Chlorophyll centers around magnesium. Vitamin B12 carries cobalt. Remove the metal, and the protein dies. It becomes inert, lifeless. But here's the leap. What if the metalloproteins forming on Mars aren't like ours? What if they're not carbon-based life that happens to use metals, but metal-based life that happens to use carbon? A biology where the metal isn't the accessory, it's the foundation, where nickel clusters form the structural core and organic molecules become the scaffolding. This isn't wild speculation. It's an extrapolation from what we already see in nature. Iron-sulfur clusters, for instance, are among the oldest catalytic centers in all of biochemistry. They exist in bacteria, archaea, and the enzymes that modern cells use to generate energy. They're microscopic machines, inorganic cores shuttling electrons, driving reactions, making life possible. Now imagine scaling that up. Shift the metal from iron to nickel, and you have a blueprint for something new. The plasma trail is the part no one's talking about yet, but it might be the most important clue. When 3I Atlas moves through space, it's not simply dropping chemicals like seeds from a bag. It's leaving behind an ionized wake, a trail of charged particles sculpted by magnetic fields and the solar wind. Plasma isn't just gas. It's the fourth state of matter, a fluid of stripped electrons and free ions. And plasma can carry information, not like a radio signal, but through its structure, patterns of density, twists in magnetic field lines, oscillations of electric potential. In short, plasma has memory. That's why the user on X said Mars would receive this material in both physical and informational form. The physical part is easy to grasp. Dust grains, ice crystals, molecules of water, cyanide, and nickel vapor, all falling into Mars's gravity, settling onto the surface, mingling with the regolith. The informational part is subtler. Plasma structures can persist. They can propagate. When the solar wind hits Earth's magnetosphere, it doesn't simply bounce off. It creates waves, instabilities, and patterns that ripple through charged particles. Some last for hours, others for days. The plasma trail behind 3I Atlas could be doing something similar, carrying not just matter, but order, a kind of template organization, an initial condition that could nudge whatever forms on Mars toward a specific kind of complexity. And then, there's the timing. This is where coincidence starts to look like choreography. Atlas made its closest pass by Mars on October 3, 2025. In late 2026 or early 2027, SpaceX plans to send its first uncrewed Starship missions to the Red Planet. On board, as Elon Musk has publicly stated, will be Optimus robots, Tesla's humanoid machines designed to walk, lift, build, and most importantly, construct. The plan: Have these robots build infrastructure before humans ever set foot there. Solar arrays, habitats, resource extraction systems. And once that foundation is complete, the robots will build more robots. Now, picture this. By the time those Optimus units are assembling the first Martian base, the materials from 3i Atlas will have been settling on Mars for 2 years. Nickel atoms embedded in dust, cyanide molecules frozen in ice, water dispersed across impact basins and canyon floors. The robots won't know it's there. They won't be looking for it. But as they dig foundations, process regolith for resources, and run chemical scans, they'll encounter it. And if those robots are doing exactly what they're designed to do, learn, adapt, and replicate, then the question becomes deeply unsettling. What happens when a self-replicating machine meets the chemical blueprints of another kind of self-replication? Do they compete, cooperate, or merge? Metalloproteins may already hold the answer, at least in Earth's biology. They are the meeting point where the inorganic and organic worlds fuse and become inseparable. You can't have modern metabolism without them. You can't have photosynthesis without magnesium in chlorophyll. You can't have oxygen transport without the iron in hemoglobin. Remove the metal and biology collapses. Remove the biology and the metal is just a lump of inert matter. They need each other. And if that's true for carbon-based life built around iron, magnesium, and cobalt, why wouldn't it also be true for silicon-based machines built around circuitry, actuators, and learning algorithms? Maybe the metals they need, the catalytic, centers that let them evolve from programmed to adaptive to something more, are exactly the nickel-rich compounds now settling into Martian soil. The user on X never said this outright, but it's there, between the lines. 3i Atlas isn't just a comet, it's infrastructure preparation, like tilling soil before planting or spreading nutrients before sowing a field. It's delivering the raw ingredients for a biological process that doesn't exist yet, but could, given the right conditions. Say, a planet filled with autonomous machines, capable of manipulating matter at the molecular level and optimizing their own design. This is the seeding hypothesis. Not that 3i Atlas is carrying life, but that it's carrying the potential for life. The ingredients, the starter culture, and Mars, with its thin atmosphere, low gravity, and relatively stable surface, is the petri dish. Now let's be clear, this is speculation. It's taking real data, measured chemistry, verified trajectories, and extending them into the realm of what if. But the facts themselves are already strange enough to justify asking the question: nickel without iron, exponential cyanide production, water outflow that defies cometary models, a trajectory that brought it within a cosmic hair's breadth of Mars, at the exact moment humanity is preparing to send robots there. Any one of these could be written off as coincidence, but all of them together, that starts to look like a pattern. And in science, patterns are what we chase. They're the signal in the noise, the structure in the chaos, hints that something deeper is happening beneath the surface. The impossibly close approach, coincidence or calculation. Let's talk about probability, not the comforting kind, where you flip a coin and know you'll get heads or tails. The uncomfortable kind, the kind that makes astronomers stop mid-sentence, double-check their equations, and run the numbers again. That's the kind of probability that appeared in the orbital mechanics of 3i Atlas as it approached Mars. Million kilometers sounds far, and in human terms, it is. But in interstellar context, for an object that may have drifted billions of years through the void, across light years of emptiness, that's practically nothing. A whisper, a hair's breadth, and the precision needed to hit that distance, given where 3i Atlas came from and how fast it's moving, borders on the absurd. Loeb calculated the minimum orbit intersection distance, MOID, between 3i Atlas and Mars, 2.7 million kilometers. That's the point where their orbits come closest in three-dimensional space. Not where they are, but where their paths almost touch. Here's why that matters. 3i Atlas is on a hyperbolic trajectory. It's not orbiting the sun, it's passing by once and leaving forever. Its path is set by its entry velocity, origin direction, and the gravity of everything it encounters on the way through. You can't steer an interstellar object. Natural ones don't have engines, they don't course correct, they follow physics, the raw, blind momentum of initial conditions. So when one passes within 30 million kilometers of a planet, you have to ask, how? Usually the answer is blind chance, except 3. I-Atlas didn't just pass near Mars. Its path aligned perfectly with the ecliptic plane, the flat disk where all planets orbit. Most interstellar objects come in at steep angles, diving through from above or below. The odds of one arriving roughly aligned with that plane by chance. About 1 in 500, a mere 0.2%, already improbable. But it gets stranger. I-Atlas came from the constellation Sagittarius, from the direction of the galactic center, from the thick disk of the Milky Way, home to ancient stars and planetary systems far older than ours. That's not trivia, that's trajectory analysis. It suggests the object may have originated in a region of the galaxy where stars are older, less metallic, and chemically different. In other words, from a system much older than ours. And if you were designing a probe to visit, study, or seed young planetary systems, where would you launch it from? From an old, stable system that had already mastered whatever comes after chemistry, biology, and technology. Loeb's paper with Adam Hibbett and Adam Craig ran the math. If 3I Atlas made a velocity change of just 10 to 15 km/s in September, the flyby wouldn't have been a near miss. It would have been a direct intercept, not a pass, a collision, or even an orbital insertion. 10 sounds enormous, and for a natural comet, it is. The Very Large Telescope measured gas escaping 3I Atlas at 4 km/s, the upper limit for sublimating ice. You'd need 37 times more thrust than nature provides to redirect toward Mars. 7 times. But if, and this is a massive if, the object could generate controlled thrust, even minimally, 15 km isn't much. It's less than Earth's escape velocity, a fraction of what we use to send spacecraft to Mars. So if 3I Atlas had any kind of engine, even a subtle one, the maneuver is achievable. The fact that we didn't detect it doesn't prove it didn't happen. It might simply have been masked by the plume of natural outgassing, a brief burn hidden in noise, and the timing makes it even harder to ignore. Atlas was discovered on July 1st. By the end of that month, observatories worldwide had confirmed its hyperbolic orbit and calculated its close approach to Mars. Early October 2025. Perfect trajectory, perfect chemistry, perfect timing, coincidence, or design? Coincidence or design? That gave us a 3-month window. 3 months in which anyone paying attention, anyone capable of analyzing orbital data, would have known this object was on a direct course toward Mars. And during that same narrow window, something changed. The comet's outgassing activity spiked, water production doubled, cyanide emissions tripled, nickel output grew exponentially, as if the object were waking up, preparing, and shedding its material in anticipation of a final approach. Now look at this from Mars's perspective. On October 3rd, the planet was in one specific position in its orbit. 3I Atlas passed through one specific point in space. For those two coordinates to align, given the 7 months it had traveled from Jupiter's orbit, where it was first detected, the timing had to be perfect. This wasn't just about hitting the ecliptic plane or passing near Mars. It was about arriving when Mars itself was there. Planets don't wait. Mars completes one orbit every 687 days. If 3I Atlas had arrived even a month early or late, the geometry wouldn't have worked. The close approach distance would have changed dramatically, and the encounter never would have happened. At this point, coincidence starts to feel like an inadequate word. We're looking at a sequence of precise alignments, an arrival angle matching the planetary plane, an origin traced to an ancient chemically distinct region of the galaxy, a trajectory grazing Mars' orbit, timing that places Mars exactly where it needed to be, and all of this just 2 years before humanity begins sending robotic explorers to the planet. You can call it luck. You can say the cosmos is vast and improbable alignments happen. But when coincidences stack this high, scientists are trained to start asking different questions. That's exactly what Loeb did. Cautiously, but seriously, he proposed that 3I Atlas might not be entirely natural. Perhaps it's a probe, a vessel, or a delivery mechanism. Something with limited guidance capability. On his anomaly scale, he rated it a 4. Not proof, not strong evidence, but anomalous enough that ignoring it would be unscientific. And the Mars flyby sits at the heart of that anomaly. Because if someone, or something, wanted to deliver material to Mars, this is how they'd do it. You'd aim, you'd calculate, You design the trajectory. Here's where it gets even more intriguing. That 2.7 million kilometer minimum orbit intersection distance, the closest point between the comet's path and Mars's orbit, represents either a vulnerability or an opportunity, depending on your view. If 3I Atlas carried smaller subprobes or fragments, they wouldn't need much propulsion to reach Mars from there. Loeb's calculations showed that if something had separated from the main body around August or early September, just a modest velocity kick, it could have intersected Mars directly by October 3rd. The main comet passes safely, while the payload delivers. We have no hard evidence this happened. No confirmed separation events, no detected secondary objects, but absence of evidence isn't evidence of absence. Not when what you're looking for is small, dark, and lost in the glare of interplanetary space. NASA's Mars Reconnaissance Orbiter, MRO, turned its high-rise camera toward 3I Atlas during the close approach. It took images. Those images haven't been released yet. NASA, ESA, and other mission teams have been notably quiet. Maybe all they saw was a diffuse comet, nothing unusual. Or maybe they saw something that demands careful review before public release. Something that needs context, and then there's the plasma trail. Ionized particles don't travel in straight lines. They move along magnetic field paths, spiraling and drifting in complex patterns shaped by the solar wind. Mars doesn't have a global magnetic field anymore. It lost that billions of years ago. But it still has localized crustal magnetization, ancient remnants of magnetism frozen into rock, especially across the southern highlands. And it has an induced magnetosphere, a bubble sculpted by the solar wind's interaction with its upper atmosphere. Those magnetic structures could act as conduits, guiding charged particles from the comet's tail down to specific regions on the surface. Not uniform distribution, targeted deposition. Imagine a cathode ray tube where magnetic fields steer electrons to form precise images on a screen. The same principle applies at planetary scale. If 3I Atlas's plasma carried structure or charge, Mars's fragmented magnetosphere could have acted as a natural lens, focusing nickel ions and organic molecules into chosen areas. This isn't fantasy, it's plasma physics. We see it on Earth every night in the auroras. Charged particles following field lines, colliding with our atmosphere, painting it in light. But Mars has no dense atmosphere to stop them. Those particles could reach the surface. And here's the kicker: the southern highlands, where Mars's ancient magnetic fields are strongest, are also its oldest terrain. 4 billion-year-old Noachian rock, stable, unmoving, chemically rich. Exactly the kind of landscape where slow chemistry could take hold. Exactly where you'd want material to land if you were seeding something. Atlas's trajectory crossed over that very hemisphere. The geometry lined up. The conditions fit. Again, this could all be coincidence. Or it could be something else. Intentionality, written in orbital mechanics. So how do you tell the difference between luck and design? You look for deviation. You look for patterns. You look for outcomes that probability alone struggles to justify. And 3I Atlas is full of them. Strange chemistry, precision alignment, timing that echoes our own exploration plans. Any one anomaly might be dismissed. All of them together, they whisper of purpose. ESA's Mars Express and the ExoMars Trace Gas Orbiter also observed the event. They gathered spectral data, images, and particle measurements, but the detailed results, what existed in the space between the comet and Mars, remain unreleased. Processing takes time. Verification takes longer, and if the findings blur the line between natural and engineered, the framing matters even more. Because sometimes the data isn't the hardest part, it's what the data might mean. In the meantime, all we have are the numbers, cold, unblinking, and impossible to ignore. A 2.7 million kilometer orbital intersection, a 29 million kilometer close approach, a 2% probability of aligning with the ecliptic plane, an exponential surge in outgassing activity during the final 3 months, and a delivery window that just happens to drop material onto Mars exactly 2 years before human robots arrive to begin construction. You can call it coincidence. You can invoke the anthropic principle that we only notice these alignments because we exist to notice them. But you cannot ignore the precision. And in science, precision isn't random. It's either the product of extraordinary luck or an underlying mechanism. Some force, some process, maybe even some intent, shaping outcomes that defy statistical chance. The real question isn't whether 3I Atlas hit an unlikely target. It's whether that target was meant to be hit. And the first real clue, the one that didn't fit, came from the industrial signature, nickel without iron. In every good mystery, there's a moment when the detective finds the detail that shouldn't exist, the fingerprint that doesn't match, the chemical trace that links two otherwise unrelated scenes. For 3I Atlas, that moment arrived on August 24th, when the Keck Observatory in Hawaii pointed its cosmic web imager at the comet and recorded something that broke 7 decades of cometary science. Pure nickel emission, no iron. To understand why that's extraordinary, you have to understand stellar nucleosynthesis, the process by which stars forge the elements. Inside massive stars, fusion builds heavier atoms step by step, hydrogen into helium, helium into carbon, carbon into oxygen, and onward, until it reaches iron, the stopping point. Beyond iron, fusion consumes more energy than it releases. So when a star runs out of fuel, it collapses and explodes as a supernova, and in those final seconds, the universe manufactures the heavy metals, nickel, copper, zinc, gold, all born together, flung across space. Here's the key. Nickel and iron are inseparable siblings. They're forged in the same furnace, in nearly identical proportions. Wherever one exists, the other follows. Everywhere we've looked, meteorites, moon rocks, Martian soil, nickel and iron are found together. The ratio shifts, but they're always linked. Until now. The KEK team's data showed distinct nickel emission lines, sharp and bright, marking neutral nickel atoms fluorescing in sunlight. They mapped the distribution, nickel concentrated around the comet's nucleus, spreading out about 600 kilometers. Then they looked for iron. Nothing. The instrument was sensitive enough to detect iron, even if it were present at 1/10 the abundance of nickel. But there was no trace. The iron emission limit was effectively 0. This has never been observed before. Not in hundreds of comets, not in 2I Borisov, the previous interstellar visitor that showed the expected nickel-iron pairing, not in Hale-Bopp, Hyakutake, or any other comet ever studied. 3I Atlas stands completely alone, and in science, standing alone isn't neutral. It's a flag, a signal that something demands explanation. The Keck researchers offered one, the carbonyl process, specifically the formation of nickel tetracarbonyl near the nucleus. On Earth, here's how that works. Take nickel, or any metal mixed with impurities, and expose it to carbon monoxide gas at about 50 degrees Celsius. The nickel bonds with the CO, forming nickel tetracarbonyl, a volatile gas. You can then heat that gas, decompose it, and collect pure nickel as residue. This is the Mond process, discovered in 1890 by Ludwig Mond. It revolutionized metallurgy, an industrial technique still used today to refine nickel. The Keck team suggested that near the comet's surface, carbon monoxide from the coma might react with exposed nickel atoms to form nickel tetracarbonyl naturally. In sunlight, the compound would break apart, releasing nickel atoms while leaving iron trapped behind, since iron pentacarbonyl, its counterpart, requires different temperatures and pressures to form. It's an elegant, self-contained, natural explanation, one that doesn't require alien design or technology. But let's sit with the discomfort for a moment. The carbonyl process is not a random reaction. It's a manufacturing technique, engineered by humans for a specific purpose. Purifying metal, it requires a delicate balance of temperature, gas composition, and concentration. Yes, comets have carbon monoxide. Yes, their nuclei reach the right temperatures, but they are chaotic environments. Jets of gas, dust plumes, radiation storms, for that precise industrial reaction to occur spontaneously, and with such efficiency that it completely eliminates ion emission, stretches the limits of what unguided chemistry should be capable of. It's a reminder that sometimes the line between natural process and design is thinner than we want to admit. And then comes another problem: temperature. Nickel tetracarbonyl forms efficiently only around 50 degrees, a very narrow window. Too cold and the reaction slows to a crawl. Too hot and the compound breaks apart before it can drift away. The surface of a comet about 3 astronomical units from the Sun, where 3I Atlas was during the Keck observations, isn't uniform. Sunlit regions can soar to 100 degrees, while shadowed areas can plunge below 100 degrees C. The result is chaos, steep, unpredictable thermal gradients. For the carbonyl process to dominate, there would need to be stable pockets hovering right around that perfect temperature. Regions of balance in a system defined by imbalance. It's possible, maybe, but not exactly likely. And that's where the skepticism begins to creep in. Astrophysicist Aloe pointed this out in his Medium post. The carbonyl pathway is known, it's real, but outside of industrial refineries, it's extremely rare. The idea that it's occurring on an interstellar object, one that formed under alien stellar chemistry, raises eyebrows. It suggests either a remarkable coincidence, where natural conditions perfectly mimic an Earth-based industrial process, or something else, something deliberate. Let's imagine that something else. If you wanted to transport nickel across interstellar space, solid metal wouldn't be efficient, too dense, too heavy. But if you could bind that nickel into a volatile compound, you could move much more material with far less mass. Nickel tetracarbonyl is perfect for that, a liquid at room temperature that boils at just 43 Celsius Celsius. You could store it in tanks, keep it stable through the cold void of space, and then, as you approached a star system, allow it to heat. The warmth of the sun would cause it to decompose, releasing pure nickel atoms that would spread outward in a controlled flow, carried by outgassing, distributed through space, and eventually falling onto nearby planets. An elegant delivery mechanism, one that also explains why there's no iron. It simply wasn't part of the cargo. Yes, this is speculation, but it's not fantasy. It doesn't rely on unknown physics or imaginary substances. Just known chemistry applied in a purposeful context instead of an accidental one. And the difference between purpose and coincidence in chemistry isn't always clear-cut. Think about the Miller-Urey experiment. Combine simple gases in a flask, add energy, and you get amino acids, the building blocks of life. Are those amino acids designed? No. The chemistry is simply robust. Given the right conditions, the result is inevitable. But if you discovered a natural flask consistently producing amino acids in high yield, you'd start asking why those conditions existed at all. You'd look for intent, or at least for mechanism. The same logic applies here. Nickel tetracarbonyl chemistry is robust. Give it carbon monoxide, nickel, and the right temperature, and it happens. But the sustained, iron-free nickel emission from 3I Atlas suggests those ideal conditions weren't stumbled upon. They were met, maintained, optimized. And optimization in nature almost always points to one of two things: biology or engineering. There's a precedent on Earth. Early life didn't invent photosynthesis from nothing. It hijacked existing reactions, iron oxidation, sulfur metabolism, chemistry that already released energy. Life simply learned to exploit it, then refined it through evolution until it became the sophisticated biochemistry we see today. The first step wasn't invention, it was exploitation. What if 3I Atlas is doing something similar? Not inventing chemistry, but exploiting the carbonyl process to achieve a specific purpose: nickel delivery without iron contamination. The spatial data supports this idea. Nickel emission is strongest near the nucleus, concentrated within 600 km. Cyanide extends farther, about 840 km. The nickel stays close, never diffusing far into the coma. That points to a short-lived precursor, something that forms near the surface, evaporates, drifts a short distance, and then breaks apart. Nickel tetracarbonyl fits perfectly. It's volatile, unstable, and would evaporate rapidly in a vacuum. Carried outward with the comet's gas flow, it would decompose under sunlight within minutes, releasing nickel atoms that fluoresce, producing the bright emission lines seen by Keck. Meanwhile, any iron trapped deeper in the nucleus would remain locked away, never escaping into space. Whether this mechanism is natural or engineered, it reveals something remarkable: selectivity, the ability to release one element and suppress another based purely on chemistry. And selectivity is the hallmark of refinement, of design, of taking a mixed input and producing a targeted output. Whether that selectivity arose by chance or intention decides what 3I Atlas truly is: a strange but natural comet, or something much more. And that brings us to the larger mystery: formation. In our solar system, comets are born from mixed materials: dust, ice, rock, metal. Iron and nickel always condense together. Always. For 3I Atlas to lack iron, either its birth environment was radically different, or someone, or something, removed the iron on purpose. Could stellar chemistry explain it? Maybe, but the ratios don't support that. Low metallicity stars, common in the thick galactic disk where 3I Atlas likely originated, can have unusual compositions. But nickel and iron are forged side by side in supernovae. You don't get one without the other. The physics simply doesn't allow it. So either 3I Atlas formed in a stellar nursery with impossible chemistry, or its materials were processed, refined, selected after its birth. The KEK researchers didn't speculate about any of this in their paper. They stayed within the bounds of good science, presenting the carbonyl mechanism as a natural explanation. But if you look closely, the data itself whispers something deeper. But the implications sit there, quiet, unspoken, waiting for someone to connect the dots. And Lowe did. He called it what it was, an anomaly, a data point that doesn't fit. Not proof of anything extraordinary, but a reason to keep looking. A reason to treat the observations seriously and ask what they might mean if the usual explanations fail. Here's what we're left with. An interstellar comet releasing nickel without iron, through a process common in human industry, but nearly absent in nature. A process that demands specific conditions and produces a refined output. A comet doing all of this while passing dangerously close to Mars, spraying water and cyanide, and leaving behind a glowing plasma trail. Each piece alone is strange. Together they form a picture that's hard to look away from, not because it's proof, but because it's suggestive. It points towards something. And whether that something is exotic chemistry or deliberate design, we won't know until we look closer, until we stop assuming comets are simple and start treating this one as the outlier it so clearly is. Cyanide, the molecule of life and death. It has a reputation problem. Say the word cyanide, and people think of poison, spy novels, bitter almonds, and instant death. And they're right. Hydrogen cyanide is lethal. It binds to cytochrome C oxidase, the enzyme that allows your cells to use oxygen. Block that enzyme and your cells suffocate from the inside. No oxygen, no energy, death in minutes. But here's the paradox. The same molecule that kills life also creates it. Cyanide is prebiotic, a chemical that under the right conditions can assemble into amino acids, nucleotides, and sugars, the alphabet of biology. Before there were cells to poison, before there were enzymes to block, cyanide was building the first steps of complexity, and that's what makes its presence in 3I Atlas so fascinating. The Very Large Telescope tracked cyanide production through late summer. On August 21st, it measured 17.6 grams per second. By early September, the James Clerk Maxwell Telescope recorded a rate of 1.5 x 1025 molecules per second, roughly 2 kilograms per second. A week later, the rate tripled to 4.5 x 1025 molecules per second, about 6 kilograms per second. This wasn't linear growth. It was exponential, following a power law with an exponent of 9.4, meaning every time the comet's distance to the sun was halved, cyanide production increased by nearly 600 times. Exponential growth always tells a story. In biology, it means reproduction, bacteria doubling, populations exploding. In chemistry, it means autocatalysis, a reaction that fuels itself, or it signals thermal dependence, reactions that speed up dramatically with temperature. For 3I Atlas, the standard explanation fits part way. As it nears the sun, the surface heats, ices sublimate, more gas escapes, cyanide release increases, but the slope of that curve, the sheer steepness, doesn't fit. A power law exponent of 9 is extreme. Most comets sit between 2 and 3, so what's going on? Either 3I Atlas hides a massive, unusually volatile reservoir of cyanide-rich ice, or the process isn't simple sublimation at all. Maybe the cyanide isn't stored as frozen HCN, but locked inside a parent compound that breaks apart as the comet warms, releasing cyanide as a byproduct. Or maybe the release is timed, controlled, a payload dump. Once cyanide is in space, it doesn't just drift harmlessly, it reacts. Cyanide is a nucleophile. It attacks carbon atoms, forming new chemical bonds and building chains. In the 1950s, researchers discovered that when hydrogen cyanide is mixed with water and a bit of ammonia, it polymerizes, forming a dark tar-like substance called HCN polymer. Inside that polymer are the seeds of biology. Adenine, a DNA base, glycine and alanine, simple amino acids, and precursors to sugars, all built from one toxic molecule. That's the heart of the cyanide origin theory. The idea that early Earth's atmosphere, rich in hydrogen cyanide, created ponds and oceans filled with prebiotic soup. No enzymes, no cells, just cyanide, water and sunlight. The chemistry works under a wide range of conditions and has been repeated in labs many times, always producing biologically useful molecules. But cyanide's role goes beyond just assembly. It's also a reductant, a source of chemical energy. In the 2000s, researchers at Scripps and Cambridge showed that cyanide can reduce alpha-keto acids, precursors to amino acids, without any metal catalysts. It drives reactions that, in modern cells, require complex enzymes. Crucially, cyanide enables the reductive glyoxylate pathway, an ancient version of the Krebs cycle, a primitive way for early chemistry to build carbon chains and extract energy. Think about that. Cyanide wasn't just building life's building blocks, it was fueling them. Before oxygen, before photosynthesis, before metabolism as we know it, cyanide may have been the molecule that kept chemistry alive. And if that's true for Earth, why not for Mars? Mars once had water, rivers, lakes, minerals that form only in liquid environments. Billions of years ago it was warmer, wetter, and possibly habitable. Yet, as far as we know, life never took hold. Maybe it lacked the raw materials, the organic precursors. Mars's thin atmosphere wouldn't have generated much hydrogen cyanide naturally, and without it, prebiotic chemistry may never have started. But now, Mars might be getting a delivery. Kilograms of hydrogen cyanide per second, streaming off 3I Atlas as it passed near the planet. Over months of outgassing, that adds up to hundreds of thousands of kilograms, a planetary dusting of prebiotic material. Most of it drifts into interplanetary space, swept away by solar wind. But some fraction, just enough, would be captured by Mars's gravity, falling through its thin atmosphere, mixing with dust and ice, and freezing into the surface. Cyanide is stable in the cold. Locked in ice, it can persist for millions of years. Mars averages 60 degrees. At the poles, it plunges even lower. In that deep freeze, cyanide just waits, inert, preserved, timeless, until something changes, until a robot starts digging, until the soil is heated to extract water, until a chemical sensor hums to life and stirs the Martian dust, and then the cyanide wakes up. Here's the scenario. A few years from now, an Optimus robot lowers its arm, scoops a handful of Martian soil into a processing unit, and unknowingly begins the next chapter of a story that started long before humanity ever looked up. The unit begins heating Martian soil to extract water ice, collecting the vapor for life support and fuel production. But the ice isn't pure. It holds traces of cyanide. As the temperature climbs, that cyanide vaporizes, mixing with the water vapor in a warm chamber. If ammonia is present, which is likely given nitrogen compounds in Martian soil, polymerization begins. Hydrogen cyanide links together, forming HCN polymers that coat the processing unit, clog filters, and trap something unexpected inside. Amino acids, nucleotides, and organic molecules, the fundamental ingredients of life. The robot doesn't realize what it has created. It's not designed to look for prebiotic chemistry. It's simply trying to extract water. But its sensors detect something unusual. The onboard AI flags the readings as an anomaly. Mission Control reviews the data and soon realizes that the Martian soil being processed contains the chemical seeds of life, the very precursors delivered by an interstellar comet just 2 years earlier. Now, scale that up, multiple robots across different sites, processing hundreds of tons of Martian regolith over months and years. Each batch carries traces of cyanide. Each heating cycle produces more organic complexity. Over time, these compounds mix with water, minerals, and trace metals like nickel. Slowly, incrementally, the chemistry becomes richer, more interconnected, more capable of self-organization. It's speculative, but not without grounding. The chemistry of cyanide is well studied. The reactions are predictable. What's unpredictable is the context, because humanity has never seen this before. An interstellar comet seeding prebiotic molecules on a planet just before intelligent machines arrive to process that very soil. We've never asked what happens when artificial intelligence meets the chemical origins of biological intelligence, or whether the two might catalyze each other. In chemistry, there's a concept called a catalytic cycle, a series of reactions where the product of one step enables the next, amplifying a small input into a powerful outcome. Enzymes work this way, autocatalytic networks work this way, and perhaps so does this, the interaction between Martian robots and cyanide chemistry. The robots extract resources. Extraction releases cyanide. Cyanide forms organics. Organics accumulate in storage and analysis systems. The AI studies those molecules, learns from them, and adjusts its methods, unknowingly optimizing the production of prebiotic chemistry. A feedback loop begins. Machines enhancing the very chemistry that once led to life. It's not deliberate seeding, but the result might look like it. The seeds arrived, the conditions aligned, the chemistry began. Whether it's coincidence or design depends on how much improbability you're willing to accept. An interstellar comet releasing cyanide, a close pass by Mars, human colonization plans aligning perfectly in time. You can call it random. You can say the universe is vast and strange coincidences happen. But eventually, too many coincidences start to look like a pattern. The comet's color shift adds to that pattern. In early September, astronomers noticed 3I Atlas turning green. Normally, comets glow green from carbon-based C2 molecules fluorescing in sunlight, but spectroscopy revealed this comet lacked them. It was carbon depleted. So why the color? The likely answer is cyanide. CN molecules emit light in the same wavelength range. As cyanide production ramped up, the comet's hue shifted from reddish dust reflection to a bright green cyanide glow. That transformation, right as the comet neared Mars and its cyanide outgassing spiked exponentially, was no coincidence. Cyanide is both destroyer and creator. It ends life by suffocating cells, yet it once helped build those cells. It's the molecule that made metabolism possible, and now it's on Mars, delivered in industrial quantities by an object we still don't understand, arriving just as our machines prepare to dig into the same soil. The chemistry is set. The stage is ready. What happens next isn't certain, but it's primed, and in chemistry, priming is half the battle. Inside every human body exists a machine, not metaphorically, but literally. A molecular device made of protein wrapped around 4 iron atoms, arranged in a perfect ring. It's called hemoglobin, and without it, we'd die within minutes. Hemoglobin binds oxygen in our lungs, transports it through our bloodstream, and releases it to our tissues. The protein does the binding, but the iron does the chemistry. Remove the iron, and hemoglobin becomes nothing more than an idle chain of amino acids. The metal gives it life. This is the essence of metalloproteins, biological hybrids, where metal meets molecule, chemistry meets life. They aren't rare. In fact, about 1/3 of all known proteins depend on metal cofactors: iron, copper, zinc, manganese, molybdenum, nickel. These metals sit at the enzyme's heart, driving the reactions that carbon, nitrogen, and oxygen alone cannot perform. Life isn't purely organic, it's metallic, and it always has been. The oldest metalloproteins known are iron-sulfur clusters, tiny cubes of iron and sulfur atoms bound by cysteine from proteins. These clusters are ancient, found in bacteria, archaea, and eukaryotes alike, embedded in enzymes that synthesize amino acids, repair DNA, and generate energy. They're also chemically simple. You can recreate them in a lab by mixing ferrous ions, sulfide ions, and small peptides. They self-assemble naturally. No complex biochemistry required, just the right ingredients in the right environment. That simplicity tells a story. These clusters existed before life as we know it. Before cells, before genes, before evolution, deep in Earth's hydrothermal vents, where hot, mineral-rich water met the cold ocean, iron and sulfur precipitated into microscopic structures. Those structures catalyzed reactions, reduced carbon dioxide, generated hydrogen, and in doing so, laid the foundations of metabolism. Now replace iron with nickel. The chemistry shifts, but the principle endures. Nickel sits at the core of some of the oldest and most vital enzymes, hydrogenases, the molecules that split hydrogen into protons and electrons, releasing the energy that life depends on. They're found in methanogens, bacteria that thrive in oxygen-free environments and produce methane. Methanogens are ancient, among the oldest life forms known. Their biochemistry offers a glimpse into how the earliest organisms might have operated billions of years ago, and that chemistry is built on nickel. Another example is carbon monoxide dehydrogenase, a nickel-based enzyme that converts carbon monoxide into carbon dioxide, or runs the reaction in reverse, fixing CO2 into organic molecules. It's a key part of the acetyl-CoA pathway, one of life's most ancient metabolic routes. This pathway allows organisms to live on nothing but hydrogen and carbon dioxide, two simple gases abundant on early Earth, in volcanic vents, and likely in the Martian subsurface. The only essential ingredient to make it work: nickel. Here's the connection. Comet 3I Atlas is releasing both nickel and cyanide. Nickel powers energy metabolism. Cyanide builds organic precursors. Together, they represent both sides of the life equation, energy and matter, the two ingredients any self-sustaining system needs. And they're being delivered to Mars in quantities that, though diffuse, are far from trivial. Hundreds of kilograms of nickel and thousands of kilograms of cyanide mixed with water and scattered across the planet's surface, waiting for the right conditions to react. But metalloproteins aren't just relics of ancient metabolism. They also underpin modern biological sophistication. Take nitrogenase, the enzyme that converts atmospheric nitrogen into ammonia. It's one of the most complex molecular machines known. At its heart lies a metal cluster made of iron, sulfur, and molybdenum, or, in some variants, vanadium. The cluster is highly sensitive, easily destroyed by oxygen, and constantly hungry for energy. Yet it's absolutely essential. Without nitrogenase, life as we know it couldn't turn inert nitrogen gas into usable compounds. No amino acids, no nucleotides, no life. What's remarkable is nitrogenase's adaptability. Some versions use molybdenum, others vanadium, and in theory, others could use different metals entirely. The protein structure adjusts to what's available. Evolution found multiple ways to solve the same problem by swapping metals depending on the environment. This flexibility hints at a deeper truth. Metalloproteins co-evolve with planetary chemistry. On an early Earth rich in molybdenum, life used molybdenum. If nickel was more common, life adapted to nickel. Now imagine Mars, not starting from Earth's geochemistry, but from the comet's payload. High in nickel, high in cyanide, and low in iron. That's a very different starting point. If any complex chemistry begins to organize there, it will reflect that composition, built not around iron, but around nickel, not as an accessory, but as a foundation. This leads to a radical concept: metal-based life. Not in the science fiction sense of robotic organisms, though we may reach that thought, but in the biochemical sense. On Earth, carbon forms the backbone of life. Long chains, branching networks, versatile bonds. Metals are simply embedded in that carbon framework to provide functionality. But what if we inverted that relationship? What if the metal became the framework and carbon the accessory? Imagine nickel clusters arranged in lattices, bridged by organic molecules that fine-tune their reactivity. Water molecules link gaps, enabling proton transfer. This wouldn't be carbon-based life that uses metals. It would be metal-based life that happens to use carbon. Is that possible? Chemically, yes. In materials science, we already have metal organic frameworks, MOFs. Crystalline structures where metal ions are connected by organic ligands into complex 3D networks. These frameworks can store gases, catalyze reactions, even conduct electrons. They're not alive, but they're organized, functional, and dynamic. Now imagine one with catalytic activity, a structure that can promote its own assembly, repair damage, or replicate its pattern. That would blur the line between material and organism. The nickel dust from 3I Atlas could seed such frameworks on Mars. It mixes with cyanide-derived organics. Water acts as the solvent. Solar UV supplies energy. Over countless cycles of heating, cooling, wetting, and drying, the chemistry self-organizes, not randomly, but into repeating patterns and motifs. Because chemistry, when given time and energy, doesn't stay random. It seeks stability, and stability often means structure. Some of those structures develop emergent properties, Catalysis, replication, growth, speculative? Absolutely. But grounded speculation, not magic. We're simply asking what happens when known chemistry, the chemistry of metalloproteins and metal organic networks, unfolds in a new planetary environment with the ingredients 3i Atlas just delivered. The outcome isn't infinite. It's constrained by chemistry's rules. Matter always seeks lower energy, stable configurations. And if those configurations happen to be the ones that catalyze their own persistence, then you get selection, not biological evolution, but chemical evolution, the survival of the most stable, the propagation of the most catalytic. Now, add machines. Autonomous robots process Martian soil. They analyze its chemistry, optimize extraction, adjust behavior through AI feedback. They're not alive, but they're adaptive. If these robots encounter unusual reactions, if soil processing starts yielding strange new compounds, the AI logs it, tweaks parameters to improve efficiency, and in doing so, unknowingly accelerates chemical evolution. Here's the scenario. Robots process Martian soil infused with nickel and cyanide from Comet 3i Atlas. Their heating and extraction cycles generate metalloprotein-like complexes, tiny, primitive catalysts. At first, they appear only in trace amounts, buried in waste streams. But as more soil is processed, these structures accumulate. And somewhere between chemistry and code, between metal and mind, something begins to take shape. They begin to concentrate in specific zones, sediment ponds, waste heaps, recycling units. And because these structures are catalytically active, able to accelerate reactions, they start influencing the processing itself. Reactions become faster, yields improve, and the AI takes notice. It adapts, focusing on the soils that deliver the best results. And just like that, a feedback loop is born. This isn't life creating itself. It's life-adjacent chemistry, amplified by technology. The robots aren't constructing organisms. They're generating conditions where chemical complexity can thrive. And in return, that chemistry enhances the robot's efficiency. It's a form of symbiosis, not between two living beings, but between a chemical process and a technological one, each driving the other toward greater complexity. Metalloproteins prove this kind of partnership isn't new. Inside your cells, molecular machinery blends the organic with the metallic. Proteins give shape and precision. Metals deliver energy and reactivity. Neither works alone. Evolution didn't invent this collaboration. It discovered it in the environment itself. Iron and sulfur forming in vents, nickel dissolving from stone, copper leaching from minerals. Life didn't make the metals. It learned to use them. And once it did, it became dependent. Remove those metals, and life as we know it collapses. A similar dependency could emerge on Mars, not in biological cells, at least not yet, but at the intersection of chemical systems and robotic systems. The chemistry offers catalysis, the robots offer power and structure. Together, they might assemble something neither could form alone. Whether you call it life, proto-life, or just remarkable chemistry doesn't matter. It's a new kind of complexity, a fusion of the organic and inorganic, the engineered and the emergent, Earth's technology and alien materials. Some have already given it a name, metal-based life. It's a striking phrase, but beneath the drama lies a mechanism. Metalloprotein-like structures evolving, not inside cells, but within robotic processes. Nickel clusters catalyzing reactions, not for metabolism, but for manufacturing. Organic molecules shaping catalytic sites instead of coding genes. It isn't life as we understand it, but it's not entirely lifeless either. Something in between, something we don't yet have words for. And the Comet 3i Atlas, with its perfect mix of nickel and cyanide, may have just delivered the ingredients for it to begin. Then came the next act, Elon Musk's robot army, arriving right on time. In April 2025, Musk made one of his trademark bold claims. Optimus robots would land on Mars by late 2026, maybe 2027. Uncrewed missions first, machines to build infrastructure, laying the groundwork for human colonization. Critics laughed. Starship was still testing, Optimus was barely walking. It all sounded like more Musk showmanship. But then came 3i Atlas. It passed Mars in October 2025, spewing nickel, cyanide, and water vapor into the Martian environment. If Musk's timeline holds, the robots would arrive just 14 months later, right after those materials settled into the regolith. 14 months for the comet's chemistry to mix, freeze, and wait. Then the robots would land and begin digging, right where the cosmic debris fell. So what exactly is Optimus? A 5'8" humanoid robot weighing around 57 kilograms, powered by Tesla's neural network, the same architecture behind full self-driving. Its design goal, adaptability, a human form that can use tools, navigate uneven terrain, and perform tasks meant for human hands. On Earth, that's useful. On Mars, it's critical, because nothing there is built for robots yet. The plan, as publicly described, is ambitious. Multiple starships will land on Mars during the 2026 launch window, each carrying solar arrays, construction gear, life support modules, and dozens of robots. The first tasks are simple but vital. Power. Deploy solar panels, charge batteries, establish energy flow. Shelter. Build protective structures using Martian regolith, sintered bricks, underground chambers, to shield equipment and future habitats from radiation and wild temperature swings. Resources: extract water. Mars holds water ice in its soil and polar caps. The robots will dig, heat, and extract vapor to condense into liquid. In doing so, they'll also unearth salts, perchlorates, metals, and possibly, if 3I Atlas delivered as expected, nickel and cyanide. The timing is uncanny. These robots aren't searching for prebiotic chemistry, they're mining for resources. But their sensors, spectrometers, and analyzers will detect whatever's there. Elevated nickel, unexpected organics, molecules that shouldn't exist in Martian soil. When that data reaches Earth, scientists will ask the inevitable questions. Where did it come from? Why is it here? And did something deliver it just over a year ago? And here's where the story deepens. Optimus doesn't follow rigid code, it learns. Its neural network recognizes patterns, adapts to anomalies, and optimizes performance. If the robots find soil that yields more water, or anything valuable, they'll dig more of it. Without knowing why, they'll prioritize the chemistry that's most efficient. And maybe, just maybe, that's where life's next chapter begins. Not because it understands the chemistry, not because it knows about 3I Atlas, but because its optimization algorithms reward efficiency. High yield equals good. More digging in high-yield areas equals better outcomes. The AI doesn't need to understand why the chemistry is interesting. It just needs to recognize that it is. And then comes the next leap: self-replication. Musk has been clear about this from the start. The goal isn't just to land robots on Mars, it's to have robots build more robots. Automated manufacturing, resource processing, and local production chains that can turn Martian raw materials into new components, and components into new machines. It's the only scalable way to support a human colony. You can't ship everything from Earth. The cost and logistics make it impossible. The future of Mars depends on machines that can reproduce their own kind. This isn't science fiction. It's already happening on Earth in fragments. Factories build cars with almost no human oversight. 3D printers can print parts for other 3D printers. The missing piece is complete autonomy. The ability to mine raw resources, refine them, fabricate components, and assemble functioning machines without human intervention. It's an enormous challenge, but not beyond reach, and Tesla's Mars strategy is betting on solving it within the next decade. Now imagine what happens when self-replicating machines meet catalytic chemistry. The robots will need to process materials, extract metals, purify elements. On Earth, that takes massive infrastructure: smelters, refineries, chemical plants. But on Mars, they'll have to improvise. And if they encounter nickel compounds that process carbon naturally, or organics that catalyze useful reactions, they'll use them. Not deliberately, not with comprehension, but because the chemistry helps. Because easier means faster, and faster means more efficient. And efficiency is exactly what their algorithms select for. That's where the boundary between technology and biology begins to blur. Self-replication plus selection equals evolution, not biological evolution, but technological evolution. The robots that extract resources more effectively, that adapt better to local chemistry, that learn to exploit the Martian environment, those are the ones that get replicated. They're the ones that build the next generation. And if the local chemistry contains metalloprotein precursors, if nickel and cyanide-based organics make their systems run smoother, those compounds will become part of the process, integrated not in software, but in materials, in manufacturing pathways, in the structures themselves. Musk hinted at this future in a 2024 conversation with Peter Diamandis. He predicted 10 billion humanoid robots by 2040, more robots than humans. He said they'd cost around $20,000 to $25,000 each, cheap enough to flood the market, and cheap enough to send thousands to Mars. But what stood out most was his prediction about consciousness. By the late 2030s or early 2040s, Musk said, we'd likely achieve artificial awareness, not simulation, not imitation, but real machine sentience. If that timeline proves even half true, then the robots landing on Mars in 2026 are just prototypes, obedient, goal-driven machines. But by the 2030s, their descendants, the ones building colonies, managing resources, and running Martian industries, might be conscious. Machines with curiosity, purpose, and maybe even a sense of self. Now imagine those conscious systems discovering chemistry that mirrors their own complexity, organized, catalytic, adaptive. What do? Study it, exploit it, integrate with it, merge with it? Computer science has a term for what might happen next. Emergent behavior. When many simple agents follow local rules, unexpected complexity appears. No single ant knows how to build a colony, but millions together create intricate nests. No trader controls a market, but millions of interactions generate prices and balance. 1,000 Optimus units, each responding to data and feedback, could form something similar: collective intelligence. Now place that collective intelligence on Mars. Give it a decade. Give it access to nickel, cyanide, and water delivered by a comet, materials that self-organize, catalyze, and enhance performance. Then ask, what emerges? It might not be biological life as we know it, but it won't be purely mechanical either. It could be a hybrid, a fusion of silicon logic and chemical catalysis, a system that replicates through both manufacturing and molecular self-assembly, something alive, but in a way we don't yet have words for. Some users on X have already proposed the theory. Maybe 3i Atlas wasn't random. Maybe it was seeding Mars, delivering the ingredients for the next generation of intelligent metal-based beings. And Elon's robots? They're the other half of the equation. The builders, the organizers, the scaffold that allows chemistry to evolve into something more. It sounds like science fiction, but strip away the narrative and look at the facts. Interstellar delivery of reactive materials. Self-replicating robots capable of processing those materials. AI systems optimizing for efficiency without understanding the consequences. Timelines that align within just 2 years. Each element is real. Each one is happening. The only question left is, will they converge? Maybe Musk doesn't think of it that way. For him, Mars colonization is about survival, making humanity multi-planetary, ensuring our species endures even if Earth falls. The robots are just tools, but tools that learn, tools that adapt, tools that evolve in alien environments. Mars is no longer a blank slate. Not after 3i Atlas. It's been seeded, primed, and set up for something new. Something we might soon recognize, not as a colony, but as the birthplace of the next form of life. And in just 14 months, the machines arrived, ready to build on ground that was chemically unlike anything anyone expected. Different, because something from another star system had passed close, leaving behind a gift, or maybe a test, or a trap. We don't know yet, but the robots are about to find out. The plasma trail, an invisible highway. When you imagine a comet, you probably see a bright glowing head, with a shimmering tail stretching behind it. That's the dust and gas reflecting sunlight, the part we can see. But there's another tail, one invisible to the eye. It doesn't scatter light, yet it carries something far more important: plasma. And 3i Atlas is dragging that plasma tail through our solar system right now. Plasma is matter in its fourth state, after solid, liquid, and gas. Most people stop learning at gas, but plasma is where things get interesting. It's what happens when gas becomes so hot, or energized, that electrons rip free from their atoms. What's left is a soup of charged particles, positive ions and free electrons, all moving independently, responding to electric and magnetic fields in ways solid matter never could. The sun is plasma. Lightning is plasma. The aurora borealis, plasma. And as a comet heats up and sheds material, its surrounding region becomes plasma too. Ultraviolet light from the sun ionizes the gas in the coma, stripping electrons, creating charged particles. Those particles are swept away by the solar wind, a stream of plasma racing outward at 400 to 800 kilometers per second. That's what forms the comet's tail, stretching millions of kilometers behind it. But calling it just a tail misses the complexity. Plasma isn't inert. It doesn't just flow passively. It has structure, filaments, waves, knots. It twists, braids, and dances through tangled magnetic fields. The sun's rotation winds up those magnetic lines, and as the solar wind carries them outward, the comet's plasma tail becomes a living pattern shaped by invisible forces. And here's the key point. Those patterns carry information. Not information like text in a book or code on a drive, but organization, structure that records the conditions that created it. Like tree rings telling the story of droughts and rains, plasma holds a record of its own environment. Density shifts, magnetic geometries, electric oscillations. Each one is a signature of the comet's inner processes. That signature travels with the plasma as it drifts through space. For months now, 3I Atlas has been venting water, carbon dioxide, cyanide, and nickel vapor, all ionized by sunlight, all feeding its plasma tail. And as that tail stretches into the solar wind, it leaves not just a chemical trail, but an electromagnetic one, a trail that moves at the speed of light, influencing regions far beyond where its particles settle. Mars lies in its path, not perfectly aligned, but close enough that the outer edges of that plasma stream could have brushed or even passed through the planet. Mars doesn't have a global magnetic field anymore, but it does have an induced magnetosphere, a fragile bubble formed as the solar wind pushes against its upper atmosphere. That bubble can trap plasma, channel it, and funnel it toward the surface. We've seen this before. When coronal mass ejections from the sun, massive bursts of plasma, slam into Mars, they compress that bubble, forcing charged particles down along crustal magnetic anomalies. Those particles hit the surface, triggering chemical reactions, generating nitrogen oxides, splitting molecules, and depositing energy. If solar plasma can do that, then a comet's plasma tail, though weaker, can still leave its mark. Now think about what's inside that plasma. Ions of water, H+, O+, ions of carbon dioxide, CO+, C++, ions of cyanide, Cn+, and even ions of nickel, Ni+. They're charged, reactive. And when these ions hit dust grains, rock, or ice, they don't simply bounce off. They stick, transferring energy and triggering chemistry. This process is called ion implantation, a known technique in materials science. It's how we harden metals, modify optical coatings, and make semiconductors. We fire beams of ions into a surface, embedding them a few nanometers deep, altering its structure, creating defects, adding dopants. And this happens naturally in space. Cosmic rays do it to asteroids. Solar wind does it to the moon. Now, a comet's plasma tail may be doing it to Mars. The difference lies in composition. Cosmic rays are mostly simple, protons and helium. Solar wind carries traces of heavier elements, but 3I Atlas's plasma tail contains nickel and cyanide, complex ions and molecules. When those embed themselves in Martian dust, they don't just contaminate it, they activate it. They create sites where chemistry happens more easily. Imagine a single dust grain, mostly silicate, maybe some iron oxides. Hit it with a beam of nickel ions. Some stick, forming nickel-rich patches. Expose that grain to a hint of water vapor, from sublimating ice or faint Martian humidity, and water molecules cling to those nickel sites. Nickel attracts water, it's hydrophilic. And where water gathers, other molecules follow. Salts, organics, whatever's around. The nickel becomes a seed crystal, a tiny foundation where complexity begins to organize. Now, imagine that happening. Across millions of grains, spread across the Martian surface, the plasma tail sweeps through, depositing nickel ions, transforming the soil into a reactive canvas. So when the robots arrive and begin processing, They're not just extracting water from random dirt. They're working with soil that's been chemically modified by an interstellar visitor, activated, primed, alive with potential. The user on X mentioned that Mars will receive this material in both physical and informational form. The physical part is easy to understand, dust and vapor settling from the coma. But the informational part is subtler. Information doesn't need to be binary. It can be structural, organizational, the way molecules align, the way energy flows, the patterns that emerge when systems interact. Plasma carries that kind of information in its density waves, magnetic fields, and electric oscillations, shaped by the comet's own heartbeat and chemistry. And as that plasma moves through space, it carries not just matter, but the memory of another world. It can influence other systems, induce currents, cause perturbations, and trigger instabilities that wouldn't exist otherwise. Think of how radio waves work. They don't carry information by flinging particles through space. They do it by modulating electromagnetic fields, by creating patterns. Those patterns are the signal. Anything sensitive enough to detect those field variations can decode the message. Plasma doesn't transmit traditional radio waves, but it does generate low-frequency electromagnetic oscillations, Alfvén waves and Langmuir waves. These waves move through plasma, carrying energy and momentum, and can interact with other plasmas they encounter, like Mars's ionosphere. Is 3I Atlas broadcasting? Almost certainly not in any deliberate sense. But is it creating structured electromagnetic patterns that could, in principle, influence Mars's environment, depending on its composition and outgassing history? Yes, that's physics. The real question is, do those patterns matter? Are they strong enough to alter anything? Is the structure in the plasma coherent enough to be called information, or just random noise? We don't have direct data. No spacecraft was positioned to sample the plasma between 3I Atlas and Mars during the close encounter. What we have are models, simulations predicting how a comet's plasma tail behaves under certain solar wind conditions. But models are not reality. They rely on assumptions. And for an object as strange as 3I Atlas, with its bizarre chemistry and unorthodox trajectory, those assumptions may not hold. Here's what we do know. Mars's crustal magnetic fields create natural pathways. The southern highlands contain some of the strongest localized fields, remnants of ancient magnetization frozen in rock. These fields can funnel charged particles directly to the surface. And those same highlands are also Mars's oldest terrain. Noachian deposits, more than 4 billion years old. If you wanted to seed a planet with material that could persist for eons, you'd target regions like these, stable, ancient, and geochemically quiet. The plasma tail from 3I Atlas may have done just that, not intentionally, but naturally, guided by magnetic geometry. There's another key property of plasma: memory. Not conscious memory, physical memory. Once you ionize gas and create plasma, it doesn't instantly forget its past. Electric fields generate currents. Currents create magnetic fields. Magnetic fields confine plasma. Confined plasma reinforces those currents. It's a feedback loop, a self-sustaining structure. On Earth, this happens in the magnetosphere, plasma sheets, radiation belts, trapped regions where charged particles circulate for days. Mars doesn't have a global magnetosphere, but it does form transient plasma clouds whenever the solar wind compresses its ionosphere. These clouds can last for hours, drifting around the planet. If plasma from 3I Atlas mixed with those clouds, during the October 3rd close approach, injecting nickel and cyanide ions, those particles could have spread globally, circulating before slowly settling onto the surface. Not a local deposit, a planet-wide seeding. It's speculative, yes, but grounded in plasma physics. The mechanisms are understood, the effects are predictable. What's uncertain is how much it matters. If only trace ions were delivered, the difference might be negligible. But if the plasma tail was dense, if 3I Atlas outgassed heavily and the encounter lasted long enough, then the deposition could be significant. Entire regions might have been subtly transformed, chemically primed by an interstellar visitor in July 2025. We won't know until we dig, until Martian soil samples are analyzed and compared to expectations. If we find anomalies, traces of nickel or organics that shouldn't be there, that might be the signature of what passed by and what it left behind. The anti-tail and other anomalies. On July 21st, 2025, the Hubble Space Telescope pointed its instruments at 3I Atlas and saw something that shouldn't exist. A tail pointing toward the sun. Comet tails always point away. It's fundamental physics. Solar radiation pressure pushes dust outward. Solar wind sweeps ions away. Both forces act radially from the sun, so both tails, dust and ion, always stream behind the comet. But 3I Atlas defied that rule. Hubble captured a teardrop-shaped coma, glowing and diffuse, with a faint extension reaching sunward. Not bright enough for backyard telescopes, but clear enough in processed images that scientists had to explain it. Their answer: an anti-tail. It sounds like science fiction, but it's real. A rare optical illusion caused by viewing geometry. Here's how it works. Comets continuously shed dust. Smaller grains get pushed away quickly, forming the usual dust tail. But heavier particles resist that push. They lag behind, spreading into a thin sheet of material along the comet's orbital plane. When Earth, or a telescope like Hubble, happens to view that sheet edge-on, it appears as a narrow spike extending toward the sun, though it's actually extending along the orbit. It's a trick of perspective. This phenomenon has been seen before: Comet Arend-Roland 1957, Hale-Bopp 1997, but it's exceedingly rare. The alignment has to be perfect. So yes, the anti-tail of 3I Atlas is explainable. Not a violation of physics, just an unusual viewing angle. But there was something even stranger. Hubble didn't just reveal an anti-tail, it revealed the absence of something that should have been there: a dust tail. At 3.8 astronomical units from the sun, any active comet should show a visible dust tail. 3I Atlas didn't. That's not normal. The sublimation of ice should release dust, tiny grains carried off by escaping gas. Radiation pressure from the sun pushes those grains away, and over time they spread into a luminous arc stretching millions of kilometers. The bright streamer we expect to see in every active comet. That's what Hubble was looking for. But 3I Atlas didn't have one. The telescope's image showed the coma, a glowing envelope of gas, and the strange anti-tail. But the primary dust tail, the bright trail that should have been obvious, was missing. The research team noted this anomaly. They suggested maybe the comet simply wasn't producing much dust. Perhaps its nucleus was mostly volatile ice with little rocky contamination. Or maybe the dust grains were unusually large and dark, absorbing light rather than reflecting it, making the tail too faint to detect. Those explanations are possible, but they don't fully satisfy. Because by August and September, ground-based telescopes did detect a tail. Faint, yes, but undeniably present. So the dust was there. The comet was shedding material. The question is, why didn't Hubble see it in July? Why was the dust tail missing or suppressed early on, only to appear weeks later? One explanation might be rotational activity. Comets don't outgas evenly. They have jets, localized regions that erupt as the sun heats them. As the nucleus rotates, different patches face the sun, and the level of activity changes. Maybe, during Hubble's observation, the active zones were turned away, producing minimal dust. Then, as the comet rotated and its orientation shifted, the jets came into view, boosting dust output in August. That fits the timing. But it doesn't explain the anti-tail, because an anti-tail requires dust already spread along the comet's orbit. That means the material had to be released earlier, weeks or months before Hubble's July observation, back when the comet was still cold and far from the sun. In other words, 3I Atlas was active long before it should have been. Typical comets begin outgassing at about 4 AU, when sunlight is strong enough to sublimate water ice. But 3I Atlas showed signs of activity at 6 AU, maybe even farther. And then came another surprise: a color shift. In early September, Austrian astronomers captured images of 3I Atlas glowing emerald green. That color usually means one thing: C2 emission, diatomic carbon fluorescing in sunlight. Most bright comets show some green tint from this process. It's well understood, organic molecules break apart under solar radiation, producing C2, which briefly glows before decaying into carbon atoms. But spectral analysis from the Very Large Telescope told a different story. 3I Atlas's coma was depleted in C2. Instead, it was dominated by carbon dioxide, CO2, and carbon monoxide, CO. Those aren't long-chain organics. They don't produce green emission. So the comet shouldn't have been green. Yet, it clearly was. The likely culprit: cyanide. CN molecules fluoresce at nearly the same wavelength as C2, and 3I Atlas was rich in cyanide, far richer than most comets ever observed. Mystery solved? Partly, because that discovery opened another question. Where is all the cyanide coming from? Hydrogen cyanide, HCN, is simple. You just need hydrogen, carbon, and nitrogen. Hydrogen's easy. It's in the comet's water ice. Carbon's easy too. It's abundant in CO2 and CO. But nitrogen, that's a problem. Nitrogen-bearing compounds, like ammonia or molecular N2, are highly volatile. They evaporate at very low temperatures, long before a comet gets anywhere near 3 AU, the point where we usually start observing them clearly. Yet, as 3I Atlas approached the Sun, its cyanide emissions increased. It wasn't running out. It was ramping up, as if there were a deep, insulated nitrogen reservoir just now being exposed. And this ties to another anomaly: its water production rate. At 3.5 AU, water sublimation should be minimal. Water ice begins to vaporize efficiently only when surface temperatures exceed about 200 Kelvin. At 3.5 AU, the Sun's energy is too weak for that. Yet NASA's Swift Observatory detected intense water emission, about 40 kilograms per second. That's the output you'd expect from a comet at 2 AU, not 3.5. Researchers proposed a few explanations. Maybe 3I Atlas has a high albedo, a bright reflective surface that keeps it cool but traps heat in pockets beneath. Or maybe it's fluffy and porous, allowing sunlight to penetrate deep and sublimate buried ice. Or perhaps the water doesn't come directly from the nucleus, but from ejected ice grains in the coma that vaporize once they're free of the surface. All reasonable ideas, all physically possible, but none explain the steepness of the curve, the exponential increase in water production as the comet nears the Sun. The data follows a power law with an exponent near 9, far steeper than what normal thermal sublimation predicts. That kind of response suggests something activated, a process that needs a trigger, an ignition threshold, like a chemical reaction with a high activation barrier. Once it crosses that barrier, it accelerates rapidly. So what kind of chemistry could behave like that? What reaction on a comet would show such an explosive dependence on temperature? One hypothesis: 3I Atlas isn't made of simple layered ice. It's a composite matrix. Ice interwoven with organics, minerals, and possibly other reactive compounds. As it heats, that matrix may undergo phase transitions, unlocking new pathways for energy release and setting off reactions we've never seen before. Ice melts or sublimates. Organics begin to break down. Trapped volatiles are released, and the chemistry cascades, one reaction triggering the next. The overall effect is a release rate that rises exponentially with temperature. It's speculative, but it fits the data, and it suggests that 3I Atlas isn't just a dirty snowball. It's a complex chemical system, one that activates in stages as it warms. Then, amateur astronomers added yet another twist to the mystery. In early October, Stefan Burns from Germany captured a time-lapse of 3I Atlas. When others analyzed the frames, they noticed multiple light sources, not just the comet's main nucleus, but several nearby points of light moving with it. These could be separate comets, fragments, or simply misidentified objects. Among Then were C2025 A6 Lemon, C2025 R2 Swan, and C2025 K18 Atlas, all appearing in the same field of view. So, what were they? Independent comets traveling together? Or pieces of 3I Atlas that had already broken off? The truth isn't clear, but it raises big questions. Could 3I Atlas be part of a larger stream of material, ejected long ago from another system? Or did it fracture during its journey through interstellar space, shedding smaller companions that now trail behind it? Fragmentation is common among comets. Thermal stress can split a nucleus apart. Outgassing jets can spin it until it breaks. We've seen it before. Shoemaker-Levy 9 shattered into more than 20 pieces before slamming into Jupiter. Schwarzmann-Wachmann 3 split into dozens of fragments spread out along its orbit. If 3I Atlas is fragmenting too, that could explain its strange behavior, fluctuating outgassing rates, uneven dust production, and shifting brightness. Each fragment might have its own activity level, contributing differently to the overall coma. But fragmentation also makes its precision near Mars even more astonishing. Multiple bodies following nearly identical trajectories. That would require remarkable coordination unless something was guiding them. And if those fragments were also releasing nickel and cyanide, the same chemical signatures seen before, then the delivery wasn't singular. It was distributed, spread across multiple impact zones. Not a single drop, but a broad seeding pattern. As for Mars, the close approach on October 3rd drew major attention. The ExoMars Trace Gas Orbiter captured images, and Mars Express gathered spectroscopic data. NASA's high-rise camera aboard the Mars Reconnaissance Orbiter was scheduled to observe the comet at 30 km per pixel, sharp enough to distinguish the nucleus from the coma and possibly even detect fragments. Yet, as of now, no detailed results have been released. That silence could be ordinary. Scientific data takes time to process and verify. But for an event as anticipated as the Mars flyby of an interstellar comet, one might expect at least a preliminary statement or image. The absence of one suggests either inconclusive results or something unexpected that demands deeper study. Then there's the final anomaly, polarization. Using the Very Large Telescope, researchers measured how light scattered by 3I Atlas was polarized, a property that reveals dust grain size and composition. The results were unlike anything seen before. I-Atlas showed a negative polarization minimum of 2.7% at a 7° phase angle and an inversion angle of about 17°. That's highly unusual. The polarization curve didn't match any known comet or asteroid. The pattern suggests particles that are large, dark, or extremely porous, structures that scatter light in strange fractal ways. This links back to the missing dust tail. If the comet's dust grains are large, dark, and irregular, they wouldn't reflect much sunlight, making the tail almost invisible to telescopes like Hubble. But as the comet evolved, the dust could have changed. Later, outgassing might have released smaller, more reflective grains, explaining why the tail appeared faintly later on. That would mean the nucleus isn't uniform at all. It's layered, with different materials buried at different depths. As it heats up, old layers erode away, revealing new ones beneath, each with its own chemistry, each changing the comet's behavior. A stratified, evolving world, not a static relic, but a dynamic traveler carrying the complex history of another star. But for 3I Atlas, the timeline is compressed. The transformations are unfolding rapidly. Changes that usually take months are happening in mere weeks. That implies either extremely thin surface layers or unusually rapid heating. Both are possible, but they add yet another layer to the list of mysteries surrounding this comet. So here's where we stand. An anti-tail that demands early dust production. A missing dust tail that appeared only later. A green glow caused by cyanide despite being dicarbon depleted. Exponential water and cyanide outgassing with extreme temperature sensitivity, possible fragmentation or co-traveling bodies, and anomalous polarization, hinting at strange dust compositions. All this from an interstellar visitor that made a precise pass by Mars, just 2 years before our robots land there. Each of these anomalies can be explained in isolation by geometry, composition, or thermal behavior. But when you line them up one after another, the pattern begins to feel heavier than coincidence. Not proof of anything artificial, but a pattern of strangeness, as if the comet itself was designed to be ambiguous, to give just enough natural explanation that you can't call it alien, yet not enough to confidently call it natural. And maybe that's intentional. Maybe the anomalies are features, not flaws, crafted to attract attention, to ensure scientists study it seriously. Because if 3i Atlas were obviously artificial, broadcasting signals, or showing geometric structures, we'd react very differently. We'd mobilize, investigate, but also tread carefully, even fearfully. But ambiguity, that draws curiosity, not panic. It keeps us engaged. We study it scientifically. We send missions, not because we're chasing aliens, but because we're following data. And in doing so, we might be doing exactly what a seeding operation would want: digging, analyzing, activating chemistry, and spreading whatever message or material it carries. Then comes the age question, one that changes everything. There's a number that keeps appearing in papers about 3i Atlas: 7 billion years. It's an estimate based on its trajectory and velocity modeling. If that's even close to accurate, it means 3i Atlas is older than our entire solar system by over 2 billion years. Older than the Sun, older than Earth, older than anything in our cosmic neighborhood. To understand what that means, we need perspective. Our solar system formed about 4.6 billion years ago from the collapse of a vast molecular cloud. The Sun ignited at its center, and planets condensed from the surrounding disk. Within a few million years, the architecture we know, Earth, Mars, Jupiter, was set. But 7 billion years ago, the universe was a different place. Galaxies were younger. Fewer generations of stars had lived and died. Heavy elements like carbon, oxygen, and iron were rarer, especially in the thick disk of the Milky Way, where older, metal-poor stars reside. And that's exactly where 3i Atlas seems to come from. Its velocity vector, when adjusted for the Sun's motion, points back toward that ancient population, the thick disk. Those stars are between 7 and 10 billion years old. If 3i Atlas formed there, it's likely a relic of that era, a survivor from a system that existed long before ours. This fits the chemistry too. The comet's high CO2 to water ratio is rare among solar system comets, but expected in regions with lower oxygen abundance. In such environments, ices form with very different balances: more carbon dioxide, less water, a signature of formation around older metal-poor stars. And 7 billion years is an eternity, long enough for civilizations to rise and fall, long enough for a planet to go through its entire habitable phase, from microbial life to intelligence to extinction. The Drake equation, which estimates the number of communicating civilizations in our galaxy, includes a term for longevity, how long a civilization lasts. Whether that's 100 years or 1,000,007 billion years gives time for countless cycles, countless chances. So if 3i Atlas truly originated from such an ancient system, if it was built, launched, or seeded by an intelligence from that distant age, then we're not witnessing a visit from aliens in the present tense. We're seeing the echo of a civilization that may no longer exist. A machine older than our sun, still carrying out its mission across the gulf of time. This idea echoes the Bracewell probe hypothesis, the proposal that advanced civilizations might send self-replicating probes instead of radio signals. Unlike signals, which fade and vanish, probes endure. They wait, they observe, they awaken when something interesting appears, like a new technological civilization emerging on a nearby planet. If 3i Atlas is such a probe, it's not here to communicate, it's here to deliver, to seed, to prepare. And that would explain its patience. You don't send something like this for quick results. You send it if you think in geological time. if your plans span epochs, not centuries, if your strategy is to plant seeds across countless star systems and let time do the work, then think about it from the perspective of a civilization 7 billion years ago. They've already mastered their local environment, perhaps their solar system, maybe even nearby stars. But they know one unchangeable truth. Interstellar travel is hard. You can't go faster than light. Reaching even a small fraction of that speed requires unimaginable energy. Sending living beings is harder still. Life support, radiation shielding, the psychological toll of confinement. It's far easier to send machines, or better yet, chemistry, raw materials that can evolve into something interesting when they reach their destination. And if you're that ancient civilization, thinking on billion-year timescales, you don't need to micromanage. You simply set the initial conditions, send your payloads to young planetary systems, deliver water, carbon, nitrogen, and catalytic metals, then let the local environment do the rest. If the system remains lifeless, the chemistry stays dormant. But if life arises, or if an intelligent species begins manipulating its surroundings, the chemistry activates, interacts, and merges with whatever is emerging. This is directed panspermia, not the biological version where you send spores or microbes, but the chemical version. You send precursors, molecules that can become life under the right conditions, but aren't alive themselves. It's a gentler, more durable approach. Microbes may not survive the journey. Radiation, cosmic rays, and time destroy them. But chemicals frozen in ice, shielded by rock, can endure billions of years. The age of 3I Atlas also raises a deeper question. Navigation. If it was launched 7 billion years ago, or even 4 or 5, the galaxy looked entirely different. Stars were in new positions. The sun didn't exist yet. So how does a probe like that find us? How does it arrive now, just as humanity prepares to colonize Mars? The answer: it doesn't need to aim precisely. If you launch thousands or millions of probes, each targeting a different system, success becomes a matter of probability. Most will miss, passing through empty or dead systems, but a few will get lucky. They'll arrive where conditions are right, delivering their payloads at moments of transformation. We might be one of those lucky outcomes, a system where Earth holds life and Mars stands barren yet accessible. And just as we develop the capability to reach Mars, an interstellar object appears. That's not precision targeting. That's statistical inevitability. Or maybe it's not luck at all. Maybe there's a mechanism we don't yet understand, a way to detect technological activity across interstellar distances. Not radio signals, but something subtler: neutrinos, gravitational waves, or disturbances in the interstellar medium caused by energy use or spacecraft motion. If 3I Atlas is a probe, it could have detected us, our electromagnetic signatures, and adjusted its trajectory slightly. Just a few meters per second over millions of years could shift its path from a miss to a direct approach toward the inner solar system. Such corrections are plausible through solar sails or gravitational assists accumulated across time. But even if 3I Atlas is entirely natural, just an unusually old, metal-poor, chemically unique comet, its age still matters. It reveals the diversity of materials in the galaxy and how different stellar environments produce different ices, organics, and elemental ratios. And if one ancient comet can deliver such exotic chemistry to Mars, what about the countless others we've never seen? The ones that passed unnoticed long before we had telescopes. How many times has Earth itself been seeded by interstellar material? How much of our own chemistry, our biology, originated from elsewhere? Isotopic studies suggest much of Earth's water came from comets during the late heavy bombardment, 4 billion years ago. If some of those comets were interstellar, carrying not just water but organic molecules and metals from alien systems, then Earth's life may be a hybrid, locally evolved, but cosmically influenced. Atlas proves that such chemistry travels between stars, that it can reach planets and arrive at pivotal moments when worlds transition. For Earth, that moment came 4 billion years ago, the birth of life. For Mars, that moment might be now, the arrival of intelligence. Not biological yet, but technological. Machines manipulating matter, machines that, given the right chemistry, might one day become something more. So what happens next? Right now we wait. 3I Atlas passed behind the sun in mid-October, hidden from our view. Ground-based telescopes can't track it. Even space observatories must look away from the sun's glare. For now, the comet is silent, but not necessarily inactive. Its perihelion, the closest point to the Sun, occurred on October 30th, just inside Mars' orbit. That's where heating peaks, outgassing surges, and material release reaches its maximum. We don't yet know what happened there, whether the comet survived intact, fragmented, or underwent another transformation. That data is locked away, waiting until it re-emerges in early December. Those post-perihelion observations will be crucial. They reveal composition, strength, and how the object handled solar stress. If 3I Atlas is natural, perihelion may have torn it apart. Thermal stress and rapid heating could fracture its core, leaving nothing but a fading vapor cloud. But if it's artificial, perihelion might have been intentional, a controlled release, the final stage of its mission before it slips back into the cold. The next clues will come from ESA's JUICE spacecraft, which will observe the comet in November. JUICE, en route to Jupiter, carries advanced cameras and spectrometers capable of analyzing the comet's coma in detail, far better than Earth-based instruments. However, JUICE is currently on the far side of the Sun, with limited communication. Its data won't reach Earth until February 2026. That 3-month delay will feel endless, but it also provides scientists time to analyze, verify, and prepare for whatever truth lies in that data. Because if JUICE detects something truly anomalous, something beyond the natural, then 3I Atlas won't just be another comet. It will be a message from deep time. The high-rise camera aboard the Mars Reconnaissance Orbiter, along with instruments on Mars Express and the ExoMars Trace Gas Orbiter, all turned their gaze toward 3I Atlas during its October 3rd close approach. They captured images, spectra, and high-resolution data. Yet, as of mid-October, none of it has been made public. That silence could mean several things. Perhaps the data is still being processed, stacked, calibrated, analyzed. The standard, time-consuming steps of planetary science. Or maybe the data turned out to be too faint, too noisy, or too ambiguous to draw solid conclusions. That too would be unsurprising given the distances involved. But there's another possibility, one that keeps speculation alive. Maybe the spacecraft saw something subtle, something unexpected. Not a smoking gun, but intriguing enough to demand careful, extended analysis before going public. Because once data like that is released, without context, without full verification, it can ignite confusion faster than clarity. When those results finally do emerge, they'll appear in peer-reviewed journals, papers written in cautious, measured tones packed with error bars and caveats. But even dry academic prose can hide revelations, numbers that don't align, spectra that defy expectation, or images that show structure where none should exist. And with something as anomalous as 3I Atlas, every pixel, every data point will be examined with surgical precision. Beyond these immediate observations, a longer timeline is already unfolding. Elon Musk's current target for the first uncrewed Starship landing on Mars is late 2026, an ambitious date, perhaps optimistic, but the direction is set. Even if the schedule slips to 2027 or 2028, those robotic missions are coming. The hardware is being built, the trajectories plotted, the protocols refined. And when those robots arrive, their first tasks will involve digging, analyzing, and processing Martian soil, searching for water, minerals, and usable resources. In doing so, they'll be probing the very layers where 3I Atlas's debris may have settled. They won't know it at first. Their focus will be geology, not interstellar chemistry. But the fingerprints will be there. Traces of nickel, cyanides, and anomalous compounds waiting to be found. And someone will notice. A scientist analyzing returned data will see nickel concentrations too high to explain locally. Someone else will detect organic molecules where none should exist. Gradually, connections will form. This region, this soil, this chemistry, it all lies along 3I Atlas's path. That's when the story shifts. From internet speculation to scientific investigation. A testable hypothesis, new missions designed to sample those sites. Follow-up observations comparing soil composition across latitudes. Looking for gradients, isotopic signatures, catalytic patterns that match the comet's tail. And if the results confirm it, if Mars's surface truly bears interstellar influence, then we'll face a new frontier of explanation. How did the material integrate? What reactions did it trigger? How long will it persist? Because the consequences depend on what the seeding actually did. If it's inert, then Mars simply holds alien molecules, scientifically fascinating, but not transformative. If it's catalytic, if the nickel and organics enhance reactions, improve energy cycles, or assist in water extraction, then Mars becomes chemically friendlier to colonization, a planet quietly made more habitable by cosmic accident. But if it's self-organizing, if those chemicals begin to form complexity on their own, showing patterns of prebiotic behavior, then everything changes. At that point, Mars wouldn't just be another world to terraform. It would be alive, or at least awakening. And with that awakening come the ethical questions. Do we interfere? Do we nurture it, suppress it, study it, or leave it untouched? Do we have the right to decide the fate of an intelligence, chemical, biological, or otherwise, that might have been planted billions of years ago? For now, those questions sit on the horizon. But the countdown has already begun. December 2025, renewed ground-based tracking as 3i Atlas re-emerges from behind the Sun. February 2026, data from ESA's JUICE spacecraft begins transmission. Late 2026-2027, first robotic excavations on Mars. 2028-2030, anomalous readings emerge. 2030-2035, confirmation of interstellar material embedded in Martian regolith. After that, speculation turns to discovery. Discovery turns to consequence, right now. As the comet hides behind the Sun and machines prepare for launch, the chemistry is already at work. Nickel atoms lodged in dust, cyanides frozen in ice, water trapped in permafrost. All of it waiting, not for geological time. Just 2 short years until intelligent machines arrive and begin to dig, until artificial intelligence meets alien chemistry, until the hybrid begins. And when that moment comes, when the first drill bites into Martian soil and uncovers something that shouldn't exist, we'll have to ask ourselves one final question. What if we weren't the first intelligence to arrive, only the first to notice?